Welcome back to Notes and Things, a podcast about ideas worth pausing for. I'm your host, Eric Verdine. Now, you've seen in the headlines, quantum computer solves a problem in minutes that would take today's fastest supercomputers the entire age of the universe. That headline is actually kind of true, but it's also wildly misleading. And the gap between those two things is exactly where today's conversation lives. My guest today is Dr. Scott Aaronson, professor at UT Austin, one of the world's leading quantum computing theorists, former researcher at OpenAI, and someone who has been at the frontier of the field since the 1990s. He's the kind of person who, when he first heard about quantum computing as a teenager, thought, and I'm pulling this directly from our conversation, this sounds like garbage, and then spent the next decades proving otherwise. Before we get into it, let me give you a 60-second primer. Here's the thing that most people get wrong. A quantum computer is not a faster computer. It's a totally different kind of computer, and for very certain types of problems. The speed difference isn't just 10 times or a million times. It's the difference between minutes and how long the universe has existed. And that's not a rounding error. That's a completely different kind of mathematics. But, and as Scott is pretty direct about this, that the only applies to a very specific category of problems. It is not a universal speed boost. It will not speed everything up. And a lot of people have been sold on a version of quantum computing that scientists themselves know isn't true. The two areas where it does give you that edge is simulating physics behind drug discovery and material science, things like better batteries, better pharmaceuticals, and breaking encryption that protects essentially everything on the internet right now, including your credit card number and Bitcoin wallets. The second one, as Scott puts it, is a big deal. Now, fair warning, the first half of this conversation is going to ask something of you. Scott doesn't dumb it down, and I didn't want him to. We go deep on how quantum hardware actually works and where the field really stands today versus where it's been hyped to be, and the specific engineering problems between here and a machine that changes the world. But I promise it's worth it, because somewhere around the halfway point, we come up for air and the conversation shifts to AI, to what Scott is genuinely excited and genuinely scared about, and to what he thinks it means that we might be creating, in his words, a new intelligence on Earth. And that's where it gets harder to shake. So get ready, buckle up, let's jump in. All right, Scott, thanks so much for joining us today. Super
Thank you. Good to be
excited.
here.
Absolutely. Super excited for the conversation. So you went from Berkeley to MIT and now you're at UT Austin. You did a stint at OpenAI, and through that, you've explored a lot of different fields, not only in your expertise of quantum computing, but philosophy and others as well. What has initially hooked you on quantum computing? How would you explain it to like the lay audience for us to start wrapping our minds around?
Yeah, well, I think I first encountered quantum computing in a popular article in the 1990s when I was a teenager. And, this was shortly after, the most famous quantum algorithm was discovered called Shor's factoring algorithm. Right. And the way that the popular articles talked about this, 30 years ago as today, was that, well, a quantum computer could just work by trying every possible answer in parallel. It would just, try every divisor of your number in a different parallel universe and then, magically pick the best one. Right. And now I was not yet a CS expert, but, I had gotten into programming. I had even learned about, what is the P versus NP question, and some of the limits of efficient algorithms. And I remember my first reaction and hearing about quantum computing was, this sounds like garbage. Okay, this sounds like some physicists who just do not understand what they are up against. Uh, and like but I had to be sure, right? I was always sort of vaguely curious about physics. But never had a good intuition for partial differential equations or things like that. I always preferred things that were discrete, which was how I got into programming, right? And I very much wanted to make my own video games. A video game seemed like, at least here's a universe that someone understands all the way down to the bottom because they created it. right? So then maybe I could understand it too, right? Um, and then the physical universe, people say all these bizarre things about it, like that, particles are not in one location. They're just in a smear of probability wave all over the place. So that just sounds like a fancy way of saying that they don't know where it is, right?
Exactly.
How am I ever gonna understand that? Okay, but, reading about quantum computing sort of, drove me to, to try to actually learn what was going on with that, right? It was this very new field in the 1990s. It looked like there was a lot of, low-hanging fruit in it, and, I think what surprised me the most was that it was not that hard to understand, the
Hmm.
basics of quantum mechanics, once you took the physics out of it. Okay. So, wha and that is what quantum computing and quantum information let you do in a certain sense, right? You forget about the details of how electrons work, how photons work, how, atomic nuclei work, like, don't get me wrong, all of that is super interesting, but you can learn that stuff later, right? You can put it off till later, okay? The first thing to learn is just, this logic of how quantum mechanics changes the rules of probability themselves. And you can describe that, using linear algebra, right? So, you need to know about vectors and matrices, and about complex numbers. Okay, but those were things that I did know, right? And and look, I regularly teach quantum information course here at UT Austin to undergrads, right? We have no physics prerequisite. I can explain all the physics that they need in the first few weeks. Okay. What we do need is, linear algebra, right? We need people, who know their way around, diagonalizing a matrix and stuff like that. And, complex numbers and probabilities. Okay, but that's math that a lot of CS majors are okay with, and then we can start explaining. What is a quantum bit? What is a qubit? What is a superposition? What are amplitudes? What is interference? Okay, what is entanglement? Right, and all these key concepts, and then you can basically fully understand, how Shor's algorithm, for example, works to factor, a 2,000 digit number, in a small amount of time where we don't know how to do that with any conventional computer. Okay, and, to make a long story short, it's not a matter of just trying every possible divisor in a different parallel universe. It does involve a gigantic superposition, okay? But, the trouble with a superposition is that when you look at it, you only see a single random outcome, right? You don't control which outcome you see when you measure. So if you just created an equal superposition over every possible solution to your problem, and then you looked, well, then all you would see would be a random solution, right? And if you just wanted a random solution, you could have picked one yourself, save the billions of dollars to build the quantum computer. So the only hope of getting an advantage from a quantum computer is to take advantage of the way that the amplitudes in quantum, which are the central numbers in quantum mechanics, work differently from probabilities that we're used to, right? A probability is a number from 0 to 1, right? Talk about a 30% chance of rain, never talk about a negative 30% chance, or much less, an I percent chance, so it's like a square root of -1 chance. Okay, but quantum mechanics is based on these new numbers, well, new 100 years ago, called amplitudes, okay, which are very related to probabilities, but they're not probabilities because these can be complex numbers. And, the basic rule in quantum mechanics is that if you want to know how likely something is to happen, so for example, how likely am I to see a photon at this place if I look for it? Or how likely will, will I see this qubit as a 1, rather than a 0, if I measure it. I have to add up the amplitudes for all the different ways that that could happen. Okay. And then you take the square of the absolute value, which gives you a number from 0 to 1, so in the end, there is a probability, right? Otherwise, we couldn't make sense of it. Okay, but the key is that the way that we calculate that probability is now totally different than what we're used to, right? It's adding up these numbers that could be positive or negative. Okay, and the result is that, like, if you have some event that can happen one way with a positive amplitude, another way with a negative amplitude, then they can cancel each other out. They can interfere destructively. So the total amplitude is 0, and then you never see that thing, right? And with every algorithm for a quantum computer, including Shor's factoring algorithm, right? The game you're playing is to try to choreograph a pattern of interference such that for each wrong answer, some contributions to its amplitude are positive, others are negative, so they're canceling each other out. Right,
So
whereas
and
only for the right
mm,
answer do you get, like, all the contributions pointing the same way.
absolutely. So, well, this is one of the reasons why practical applications is challenging
Yeah,
because you
absolutely,
have
because
you have all of these things. It's like a mist.
yeah,
It's a mist, and
yeah,
then your answer is
and
within that mist, but you have
right.
to be able to filter it out.
Right. You have to shape this mist somehow so that it concentrates more on whichever answer is the right one, right? And you have to do that even though you yourself don't know in advance which answer is the right one.
It,
Because if
it's
you
it's
already knew,
almost
what
like a
would be the point?
sandstorm. It's a
Yeah,
sandstorm
right,
of
right, right, right,
information.
right. But now if you want this to be a useful sandstorm, then you have to take advantage of some mathematical structure in your problem that's going to mean that the amplitudes will somehow pile up, on
Yes,
whichever answer is the right one, even,
yes.
which you don't know in advance, and you have to do all of that faster than even a clever classical algorithm could find the
So
answer, right? So
it's yeah.
yeah,
So
but
it's almost yeah. Go ahead.
but
Sorry.
I was actually, able to understand this, right? Because,
Yes.
in the end, it's just another model of computation, right? And,
Hmm.
in theoretical computer science, one studies all kinds of, bizarre, non-deterministic Turing machines and, all kinds of
Hmm.
things, right? So this is, another model. You can
And
learn the
another
rules
thing.
a bit. And then, once I understood that, then first of all, I was like, well, if this is how the universe works, well, then, the burden is on the people who think this is not possible, right? Like,
Mm.
if quantum mechanics works this way, then of course this should ultimately be possible. Or, if it's not possible, then that would be a revolution in physics, right?
Yeah,
So
absolutely.
that's the first thing. But the second thing was just that, they're like all the basic principles of theoretical computer science, right, that had developed over decades, you could now re-examine them, like putting it,
Mm.
the letter Q in front of everything, right? How does quantum mechanics change this, right? And so it was clear that there was just this immense, amount of intellectual, effort,
Mhm.
that
Mhm.
this was going to take. There was this sort of brand new field that was being born, and so, of course, I wondered sort of, can I do anything new there? And,
So
yeah,
it was an entirely new frontier. It's
yeah,
as if you had all of these stacks of, books of information with theories, and then you
mhm,
just took a lens that washed over it in a different color and said, "Well,
yeah.
how does it look now? And what
Very
can we do
much, very
differently?"
much, yeah. I
Yeah.
mean, there had been a few physicists, thinking about quantum computing since the early 1980s, which is when I was born, roughly, but basically, most famously Richard Feynman and, David
Mhm.
Deutsch, right? But it was just this sort of oddball idea that was just sort of off somewhere, right? And then, in the 90s, there was this sequence of developments, what was called the Bernstein-Basarani algorithm, and
Mhm.
then Simon's algorithm, and then culminating in Shor's factoring algorithm. That
Mhm.
really, for the first time, sort of made everyone face the question of, okay, what would it take to actually build this? Right. And,
Absolutely.
and are the like the basic rules that we thought, we knew for what is efficiently computable, does nature have a totally different idea? We
Absolutely.
yeah,
Well,
yeah.
so so when when the layperson sees the headlines
Mm.
and they say, "Oh, this quantum computer can solve a problem in 5 minutes that our supercomputers today would take the entire age of the universe to solve."
I mean,
Where
I think there
what
are such problems, by the way.
but
Yeah. Yeah.
it's an entirely different way
Mm.
to
Yeah.
approach a
That's
problem in
right.
general.
That's
So it's
right.
almost unfair to say it's like comparing movement. I'm going to get from point A to point B walking, or I'm going to go from point A to point B flying. It's
Yeah, but
you're
it's
getting
even more
someplace,
than
but
that.
it's not even the same
But
mode of
it
transportation.
right, right. In a sense, it's even more than that because a flying rather than walking, might mean that you get to go 500 times faster or something like that, right?
Right.
But
Right.
it's some factor, right? It's some multiple, right? And
It's you'd be
yeah.
flying so fast you'd be like mashed potatoes in the
Well, yeah.
cockpit
Look, look,
because
look, look, and look.
because you'd be crushed.
People constantly want to ask me, so then how many times faster is a quantum computer? Is it, 1,000 times faster? Is it 1,000,000 times faster? Right. And the truth is, if it were just a matter of some factor, then we would just call it a faster classical computer. Right.
So
So
is it even okay,
it's a
sorry.
different way of harnessing nature to do
Yes.
computation,
Yes.
and for some problems, it really doesn't seem to help at all. Okay, so for some types of problems, it is just as slow as a classical computer, or even slower.
Mm,
But then for
mm,
other types of problems that have the right kind of structure, such that you can choreograph this interference pattern that we were talking about before, like, you will
mm.
get better scaling behavior. Getting better
Okay.
scaling behavior means more than just, so it is some fixed factor faster, right? What it means is that, like, you could, let's say, factor a number that is n digits long
Mhm.
using only about n squared steps using a
Mhm.
quantum computer, right?
Mhm.
Whereas the fastest classical algorithms that we know for factoring an n digit number are going to need a number of steps that grows exponentially with n.
Got it.
Actually, with a
The
cube root of n. Okay, but
yeah.
so therefore, the advantage is actually a scaling advantage, right? It gets
Mhm. Mhm.
better and better as you go to bigger and bigger numbers. Okay, and
So
this is
yeah.
how you get into this territory of, the quantum computer does something in 10 minutes that classically takes longer than the age of the universe. It's because you're
That
comparing, like, n squared against 2 to the n power. Okay, and
totally.
if n is 1,000, then that becomes very, very dramatic.
Absolutely.
Yeah,
I know
yeah.
this is like a rudimentary visualization, but it
Mm.
helps me think about these things. You think of like the kid who's got um the box where they put
Mhm,
the shapes in, the
mhm.
blocks. Right? If you think of computations or a problem that you're trying to solve for as the shape or the cutout of the shape trying to go into the box, and the computer is the actual block going into the box. With a
Mhm.
quantum computer, you can basically it's an entirely different mode of doing it. So it's not even the shape or the block anymore. It's like a grain of sand. But if it
Look,
doesn't
I
fit
mean
into
I mean, look, the people have tried all kinds of metaphors, right? I
yeah,
usually just try to, explain what it is as best as I can, right? Which, I've been trying to do this for 20 years, and, I'm,
yes.
like, still, like I get,
It
every other day, I'm, talking to a journalist or to a podcaster like
yeah,
yourself, saying, like, what visual metaphor can we use to, like, explain this in one sentence? And I'm like, well, after 20 years of trying this, like,
you're still
can you give me 10 minutes?
yeah, yeah, yeah. Some of them I'm sure
Yeah,
like fall flat and they
yeah,
just don't get it. And then some of them
yeah.
land perfectly. It depends on the
Yeah,
person.
no, I mean,
It, it
different metaphors could be useful for different purposes.
Well, it's almost a
Yeah.
misnomer in a sense of using a computer because for a lay audience,
Mm.
we think of speed of computing. We
Yeah,
started up with dial-up,
yeah.
and then we had flip phones, and then we had the iPhone, and then
Well,
we had
now you're talking about speed of information transmission.
correct,
Right.
exactly, and
Another
that's what I mean
yeah,
when you see the
yeah.
headline.
Well, yeah, but no,
It's an entirely
whether
different thing.
right, whether you look at, information transmission, information storage, number of computational steps per second, all of that, of course, has been on an exponential trajectory since the
Hmm.
very early days of computing, right? And so we are sort of almost used to Moore's law by now, right?
Right. Right.
And even though it is sort of been this tide that has taken us into this very different world, right?
Hmm.
Uh,
Hmm.
but all of that progress, right, has all been sort of in the same model of what a computer is that Alan Turing and his friends knew about in the 1930s, right?
Hmm.
So like all the computers that we use today, the ones that we're having this conversation with, so forth, they could all be thought of as just Turing machines, or as like
Hmm.
the same kind of stuff that people had in the 1950s,
Hmm.
but just faster, just with more memory, with a higher bit rate. Okay, a quantum computer, I think, would really be the first useful type of computer that is not in that paradigm, right?
Got it.
Whose
Yes.
basic physical building blocks are not bits at all. They are qubits, right? They are
Hmm.
these
Hmm.
things that can be in superpositions of zero states and one states, and that is why a quantum computer could solve certain specific problems with polynomial scaling, as we
Hmm.
call it, like
Hmm.
n or n squared scaling, that with any classical algorithm, as far as we know, would take exponential scaling.
Absolutely.
So
So,
that's the promise. Um,
so in going
yeah,
back to this sandstorm
yeah.
analogy, we'll stick with that one, I think,
All right.
and trying to harness the sandstorm.
Yes.
But looking at a specific use case. So you think of
Sure.
use cases
Mhm.
for this, you hear logistics, you hear pharmaceuticals, you hear
Yeah,
finance
yeah,
to a
yeah,
degree.
yeah.
Can you walk me
Sure.
through a practitioner of
Mhm.
quantum computing who's
Yeah,
trying to solve something
yeah,
for an industry or an
yeah,
enterprise?
yeah,
Is it is it a guy or gal at a lab at a computer
yeah.
typing things in, and then they have the giant
Mhm.
quantum computer? And for
Yeah.
folks, if you wouldn't mind just quickly describing what a quantum computer looks like, because many
Yeah,
people have no
absolutely.
idea,
Okay,
but
so
it's very interesting.
there's a whole bunch of hardware platforms that are being pursued in parallel, and what it looks like depends on which one, right? But if we're talking about superconducting qubits, which for example Google and IBM are pursuing, then the main thing you see when you walk into the lab are these dilution refrigerators, right? Which are like the size of a closet. They're noisy things. Right, and they kinda look like an upside down wedding cake, right? This is because like, each
Yes,
layer of the
yes.
cake is cooling to a lower temperature than the one above it, okay? And,
Mhm,
like 4 Kelvin, 1 Kelvin, whatever, and then at the bottommost layer, you're cooling to maybe 10 millikelvin, like a
mhm.
hundredth of a degree above absolute zero, okay? That's where the
It's
chip is.
incredible.
By the way, by qubit standards, this is actually kind of hot. Okay. This is kind of this is kind of hotter than
It's
they would
so
like
I
it
mean,
to be, but
yes.
this is as cool as they can practically make it. Okay. And and then at those temperatures, what happens is that these superconducting currents start to behave quantum mechanically, right? And you start being able to manipulate them as qubits, and you can get them to interact with each other using something called a Josephson junction. Okay, and so they have this chip with with the qubits arranged in like a maybe a square grid where each qubit can interact with its nearest neighbors. And now the actual people there are just going to be sitting at classical computers, right,
Mm,
where they're controlling everything from.
mhm,
Okay, and those classical computers, running Linux or Windows or whatever, right? We're going to be sending a signal, into a microcontroller, which
mhm,
then is sending signals, into the chip inside the
mhm,
dilution fridge, and then making measurements and reading out answers, right? So, and by the way, the person, people have increasingly put these resources on the cloud, which means that
yes.
the person who is controlling the device could be on a different continent. Right,
Wow.
and these days very often would be on a different continent.
Mhm,
Okay,
mhm, mhm.
uh, um, So, just like, when you use Chat GPT, right, or
Mhm.
other services that are, provided by data centers, by GPU clusters, you have no idea where that, data center physically is, right? But, I
Mhm.
spent some time at OpenAI. Most
Mhm.
people at OpenAI have no idea where the data centers physically are, right? They're just, they're okay. But anyway, if you walk into a lab doing trapped ion qubits, then you'll see, there's like kind of a fist-sized trap where these,
Mhm.
often ytterbium nuclei are placed, and the
Mhm.
spins of those nuclei are used as qubits. So you'll see, like a lab table full of a bunch of
Mhm.
stuff, like lasers for, sometimes it kind of looks cool, right?
Yes.
Uh, uh, but yeah, so right now you see kind of like a whole room full of stuff, right? Just like,
Mhm.
in the 1950s, if you walked into, to see a mainframe classical computer, you probably see a
Mhm.
whole room full of stuff, right? That's more or less what you would see, right? And but
Mhm.
like, when I tour a lab, it's like, okay, this is really cool. It's not, I'm a theorist. It's not like I can tell anyone, oh, I think this wire is in the wrong place.
Right, right, right.
But then, what we end, the experimentalist and I would normally just end up on a whiteboard, just talking about the actual qubits inside.
Mm.
And then we're talking about amplitudes and entanglement. And, we're not talking about the things that you can directly see, right?
Mhm.
We're talking about, what's actually happening at the underlying
Mhm.
level. So yeah, so I think that the economic model for the foreseeable future is certainly
Mhm.
that, quantum computing, just gets made available as a cloud service, right?
Mhm.
We can just, use it over the standard internet. I don't see a good reason why anyone needs a quantum computer in their home, right? And of course, I'm a little nervous to say this because people said that in the 70s about classical computing, and that was, that's
Yes.
ridiculed today as one of the wrongest predictions in history. But if you look at what they were saying, they were basically talking about what today we would call the cloud, right? They were saying
Well, if
in your home, you just need a terminal. And I think that ultimately that was true, right?
yeah, and that's the
Yeah,
most that's the efficient way to go about it
yeah,
too, when you
yeah,
have
yeah.
material costs.
That's
Are
right,
you
that's right.
able to have multiple users? So if you think
Oh,
of
yeah.
a Google Doc and then you have multiple
Mhm.
users in
Yeah.
that, are you able to run a quantum computer with
Yeah, well, I
multiple
mean,
inputs?
the way that it works now, because, companies like Quantinuum, like IBM are already providing, cloud access to their, quantum computers, which have maybe 100 qubits or so, which are sort of just starting to get to the point where they're, maybe not, if not yet commercially useful, then scientifically interesting, right?
Yes.
To
Yes.
use it, so they already have customers who get, remote access and do experiments on these
Mhm.
devices, and uh, uh, um, but the other thing, to understand, okay, the main way that quantum computing has been misrepresented to the public and sort of
Mhm.
missold, right, is that, people realize that, if they want to raise huge amounts of money, then the narrative, that people will like is that a quantum computer is just going to speed up everything. Okay, it's just
Right.
going to be the next, thing like after Moore's law that just
Mhm.
speeds up every logistics problem, every financial portfolio optimization, everything
Right.
under the sun, right? And
Right.
so people started saying this, and they realized like journalists loved it, investors loved it, right? And the only problem is that like all the scientists who work in this field, we know that it's not true, right?
Yes.
Or at least, maybe it takes like tiny grains of truth and then just, exaggerates them by, by orders of magnitude,
So
right?
I'm
But yeah,
yeah, I'm laughing. I'm laughing because
yeah,
I'm thinking of the
yeah.
investors who are getting
Uh-huh.
sold, and they're like, "Yeah, I'll give 10 million," and then they
Right.
visit the lab, and
Yeah.
they see the machine,
Yeah.
and then they say, "Well, yeah, the experiment failed yesterday though because there's a slight shake."
Oh,
And they go,
yeah, yeah.
"What?"
Well, look. I mean, yeah, those are things like I'm sure that at all the quantum computing labs, they deal with every kind of mundane issue that can cause the qubits to lose their coherence, lose their quantum
Mhm.
state. Yeah, like I don't think that should even should seriously phase an investor. The thing that I think that
Right.
people have been, systematically misled about is that, they really think that a quantum computer just speeds up everything, right? And I
Mhm.
think, those of us in quantum algorithms know that, for 30 years, right, the basic situation in the field has been we know exponential quantum speedups for a few very, very special types of problems that
Mhm.
have, very, very special structure that let us choreograph this interference pattern that
Mhm.
concentrates all this amplitude onto the right answer, right? The two main categories where quantum computers give you like this exponential speedup,
Mhm.
it could really matter in practice. Okay, number one is quantum simulation. That means,
Mm.
simulating quantum physics and chemistry themselves. For example, for material science, for designing better batteries, better solar cells, pharmaceuticals,
Mhm.
high temperature superconductors, it could plausibly help with any of those tasks, right?
Mm.
And this was the original application of a quantum computer that Richard Feynman, and the other physicists had in mind in the early 80s, right? That it just,
Mhm.
like nature is giving us this lemon in like, quantum mechanics being so hard to simulate on classical computers because of the exponentiality of this wave function, of this sort of vast number of amplitudes that you need to keep track of even a small number of particles. And then they said, well, if nature's giving us this lemon, why don't we make it into lemonade? Right?
Yes.
Why don't we
Yes.
make a computer that itself would be based on the same principles? And then what would that be good for? Well, at least it would be good for simulating quantum mechanics itself better.
And,
Right? And
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 I
and,
mean,
and
and
that is a
yeah.
huge, a potential application area, right? It's not something that sort of most end users will directly care about, right? But it's certainly
Yes.
something that pharmaceutical companies, that chemical engineers, materials manufacturers, right? They all have problems involving many body quantum mechanics. Okay, so
Well,
that's yeah.
yes.
Go on.
Well, I was gonna say that is exactly what I was going to say, is that
Mm.
even those seem like a small cohort
Yeah.
of applications,
Uh-huh.
it can have massive implications
Yes.
to us. I
Yeah.
mean, material science, pharmaceuticals,
That's right.
huge,
Yeah, that's right, and, and look, in
implications.
all these fields, I mean, it's only a win if you can beat the cleverest thing that people could do with classical computers, right?
Right.
So, like, for
Right.
example, could a quantum computer help with simulating protein folding? Well, conceivably, but now whatever you do, you've gotta beat AlphaFold 3,
Exactly.
right? Which just, won the Nobel Prize in chemistry for,
Mhm.
revolutionizing protein folding just using classical computers, just using
Absolutely.
AI to find approximations that are good enough, right? So you have to win, you have to find the cases where you win against that. Okay, but I'm optimistic that there will be such cases. Okay, now the
Absolutely.
number two application was the one I talked about, that put quantum computing on people's radar 30 years ago, and that was the seminal discovery by Peter Shor that once you have a fully, programmable, error corrected quantum computer, then you could use it to break the types of public key encryption that we've
Mm.
used to protect the internet.
Mhm.
Okay, which are systems like RSA,
Mhm.
Diffie-Hellman, elliptic curve cryptography. Right, so this encompasses everything that is protecting your credit card number when you're sending it to Amazon, when you're
Mhm.
using HTTPS, right? What is protecting Bitcoin wallets, for
Mhm.
example? Okay,
Yes.
so this is kind of a big deal, right? And on the other hand, it's hard to put forward as a positive application for humanity, right?
Mhm.
It's a positive for, whichever intelligence agency or criminal syndicate,
Right.
gets the ability first, especially if no one else knows that they have it. Okay.
Right.
But in principle, we basically, already know the solution to this, which is to migrate to quantum resistant forms of encryption. Okay, so we
How
do, yeah,
yeah.
yeah.
How
So
difficult would that be then?
well, it's a giant headache logistically.
Okay.
It's sort of like in principle, we think we know what crypto systems people ought to be using instead. Okay,
Yes.
and in fact, NIST, the federal agency, had a
Mhm.
competition from 2017 until 2022 to agree on standards for post quantum cryptography, and
Mhm.
and that concluded, and they are recommending that people upgrade to these public key encryption systems that are based on what are called lattice problems. Okay, problems
Mm.
involving like high dimensional lattices of points, right? And these are problems. I mean, we can't prove that it's unbreakable by a quantum computer. For that matter, we can't prove even that any of these systems are unbreakable by classical computers, right? These
Mhm.
are all unsolved problems, but these are systems that have withstood at least like 25 years of attempts to try
Mhm.
to break them, either by classical algorithms or by quantum algorithms.
Mhm.
And so, they seem, like, yeah, they're not going to get broken without some mathematical breakthrough. And, companies like Google, various federal agencies have already started the process of migrating to these post quantum
Mhm.
crypto systems. I was at a conference about it, here in Austin a year ago, where, there were people from NIST and from the NSA, who were basically saying by 2031, they want every federal agency to have the ability to use post quantum encryption. Like by 2035, they want them to actually be using it. And like
Wow.
but by their standards, this was a lightning fast timeline.
I was
You
gonna
know,
say that was
yeah.
quite
Yeah,
fast.
like,
Th
there is no possible way it could be fast, I hope that will be fast enough,
Yes.
I'm not
So
actually sure, but yeah, but
fro
those are the 2 big cases where we get
Mhm.
exponential speedups that matter in practice, and then for 30 years, we've been trying to expand that list beyond, quantum simulation and code breaking, and,
Mhm.
the real, holy grail would be, exponential speed ups for, logistics, supply chain problems, training AI models, right?
Mhm.
And, all these other, optimization and machine learning problems
Mhm.
that we deal that, just about every large organization deals with every day. And there, to make a very long story short, we know of some modest advantages that a quantum
Mhm.
computer gives you. Eventually, it takes longer before those become a win over
Yes.
classical. But there's besides Shor's algorithm, there's another very very important quantum algorithm called Grover's algorithm.
Mhm.
Discovered in 1996, and Grover has way broader applicability than Shor's algorithm. Right, it
Mhm.
can be used for just about any hard search problem, not
Mhm.
just for factoring or for, these number theory problems.
Mhm.
Okay. But the advantage is more modest. It's like where a classical computer would take n steps, Grover's algorithm takes something like square root of n steps.
Mm.
Okay. So, so it's a quadratic advantage. We would
Mhm.
call it. Okay. So it's something, but it takes longer before that wins. And
Mhm.
then, people have been trying to get advantages for these types of optimization and AI problems beyond the Grover advantage.
Mhm.
And so there's a huge amount of research about it. My I run a group at UT where, my students try to find new quantum algorithms or, analyze existing ones. And, so there's a whole, it's a very, very long story. But I think for these types of sort of unstructured problems, most of the speed ups that we have, they're either modest, I would call them Grover-like speed ups,
Hmm.
or else they're kind of for very, very special cases of the problems that we don't know how often those special cases are going to show up in practice, in
Hmm.
situations people care about, or they're kind of speculative. Like, yeah, there might
Yeah.
be a big quantum speed up. We can't rule out that there is one, but we really don't know. We have to try it out with a large quantum computer before we really know, how well this algorithm compared, right? And one of the trickiest parts, again, is that, it's not enough to have a quantum algorithm that does something or even that does it fast, right? We only win if we are beating the best classical algorithm. That, and
That's a
classical
very, very
algorithms are a
important part.
moving target. They get to fight back, right? So like again and again in this field, it has happened that like someone will, have they'll propose a quantum algorithm, let's say for some machine learning problem or optimization problem, right? I had an 18-year-old undergrad who was involved with this, type of thing, like 8 years ago, right? Where she managed to take like one of the quantum algorithms that seemed to get an exponential speed up for a machine learning problem. It was just like recommending products to customers in a
Hmm.
Netflix like
Hmm.
situation, and she managed to dequantize that algorithm, meaning she found the classical algorithm that was almost as efficient, right?
Wow.
And so
Yes.
when someone like that comes along, then then what previously looked like a quantum speed up can
Wasn't.
vanish, right?
So that's wow, that's very interesting. It's like a turf war.
Yeah, 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 right,
The
right. But,
the
you can hope like eventually everyone wins because,
yes.
we find a faster quantum algorithm, then that inspires someone to go find a faster classical algorithm, and then we have this faster algorithm, and we didn't even need a quantum computer at all to
And
run.
that's when you get innovation. That's when you
Yeah,
get
yeah, so
innovation.
right,
That's
so
what
that
that's
so
where
that
it's healthy
that
competition.
that kind of thing has happened several times. Of course, what we would like, as quantum computing people are, cases where, the quantum computer durably wins, right?
Right, 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 right.
But and we do have, what we're pretty confident are a few such cases, quantum simulation, breaking public key cryptography, and then,
Mhm.
these more modest advantages for machine learning and optimization. As I said, we've been trying to broaden that list.
So one of the things
Good
we
luck.
see, on the layperson side, we see
Mm,
these hockey sticks of AI. Every month there's a
yeah,
new big model, new
yeah,
breakthrough, et cetera.
yeah.
Do you see does it feel like that on your end on the quantum computing side, or is it still pretty as it was 10 years ago?
It's
Or is there a
definitely.
combination exponentially just
Yeah,
growing?
so it's definitely not as it was 10 years ago in quantum
Mhm.
computing, right? I mean, 10 years ago, people had ideas for, building systems with, 50 or 100 or 200 qubits, but they hadn't actually done it. At least not
Mhm.
with good qubits, right?
Mhm.
Not with qubits that would actually maintain their state or, the kinds of, time lengths that we need, right?
Mm.
And what we've seen, and and especially, just literally within the last couple of years, right? We've
Mhm.
seen, the basic hardware building blocks finally start to work. Okay.
Yes.
At the level of reliability, that you would, where it would make sense to scale it up
Mhm.
to a much, much larger system, right? So, like, we've known, the basic theory of this for 30 years, right? And then, that theory has been, in place. It's been built upon, but, it hasn't really changed. And what that theory told us was that, okay, the good news is that, if you wanna build a scalable, quantum computer, you don't need perfectly accurate operations, right? If
Oh,
you
yes,
right,
I did
if you
read
if you
this
needed
recently. Yes.
perfectly accurate operations, that would have been a killer, right?
Mhm.
Because you'll never get that, right? You can build a reliable quantum computer even out of operations that fail with some
Mm-hmm.
probability. Okay, that's the good news. The bad news is that the probability that they fail has to be really, really small. Okay,
Mm.
uh, so basically, there are these very, very clever quantum error correcting codes that people discovered around 1995, 1996. And once you get your physical error rate below a certain threshold, then these error correcting codes can push your effective error rate, all the way down towards zero, right?
Mm-hmm.
But if you're
Mm-hmm.
above that threshold, then when you try to do error correction, you're just going to make things worse, right? It's
Mm-hmm.
just like as you try to correct errors, you're just going to be introducing even more errors as you do
Mm-hmm.
that, right?
Mm-hmm.
So,
Mm-hmm.
there's kind of like, something sort of like a critical mass for a nuclear explosion, right?
Yes.
Like, when you're halfway there, you don't get half as big an explosion, right? It just doesn't go. Right. And so,
Mm-hmm.
we sort of knew this, in the 90s that if you could get a operations on 2 qubits, at a time that were 99.9999% accurate. Okay,
Mm-hmm.
that like had only a 1 in a million level of failure, right?
Mm-hmm.
Then you could you could actually do this error correction. It would be, and then you could just keep your encoded qubits alive for as long as you needed them to be. Okay,
Mm-hmm.
but at that time, it would have been great to do just a 2 qubit operation that was 50% accurate. Right,
Mm-hmm.
right, it's like the 2 not like, okay, the good news is, it's just some number that you have to get to. The
Yes.
bad news is the number looks really, really far away, right? Okay, so now, what has happened over 30 years? Well, basically, you've had these 2 curves get closer and closer together.
Mm-hmm.
So first of all, theorists realized, oh, we could still error correct even if, we only had 2 qubit operations that were, let's say, 99.99% accurate,
Mm-hmm.
right? And
Mm-hmm.
then that became 99.9% accurate, right?
Mm-hmm.
We think, but then also the 2 qubit operations that the experimentalists could do in the lab, they went from 50% accurate to 90% accurate
Mm-hmm.
to
Mm-hmm.
95%, right? And then when Google did its quantum supremacy demo back in 2019, they were using a programmable system with 50 qubits that were, where the operations are 99.5% accurate. Right. And
Mm-hmm.
and that was what enabled them to do that demo. Right.
Mm-hmm.
And within the last year, the state of the art has actually become 99.9% accurate
Wow.
2 qubit gate.
So
So
big leap.
we're basically at the threshold, right? And that is why just within the last year or so, we've started to see like the first demonstrations of using error correction to protect a single qubit,
Mm-hmm.
where it actually works. Like you're
Mm-hmm.
keeping that qubit alive for longer than, your
Mm-hmm.
underlying physical qubits were staying alive for. You're keeping it alive for longer as you use more and more physical qubits to
Mm-hmm.
encode your logical qubit. Um, and so I think from here on out, there remains merely the staggering engineering problem of scale, taking the kind of hardware that has now been demonstrated and scaling it to where, you could shuttle around millions of physical qubits and do
Mm-hmm.
billions of operations on them.
Mm-hmm.
And no one has ever built a quantum system at that kind of scale before. Okay.
Yes.
It might fill a building, with like
Mm-hmm.
dilution refrigerators, being shuttled around. But, it's kind of like,
Yes.
the nuclear physicists like talking, spitballing about this in 1939, right?
Mm-hmm.
I guess, I think Niels Bohr said, well, in principle, if you just converted a whole country into a uranium enrichment plant, you could
Mm-hmm.
get enough, uranium-235 to build a bomb. In reality,
It's
that's that,
extraordinary to think about.
that's not going to happen for, for who knows, how many generations, right? And then, a few years later, he was, after he'd escaped to America, he was taken on a tour of the Manhattan Project, and he said, "Well, I
Mm-hmm.
see that that's what you've done." you know, you've you've
That's
you
that's
you
incredible.
you have made like
S
a large fraction of the U.S. into a uranium enrichment plant, and
Absolutely.
so
Yes.
yeah, it's now a question of just how badly do people want a quantum computer? How much are they willing to spend on it? So that's that's kind of why the field is at an exciting point right now, right? Now the but you brought up the comparison to AI, right? And
Mhm.
like the biggest difference that I would want your listeners to understand is that a quantum computer sort of dramatically speeds up a few very specific things, right?
Mhm.
And this is because of this, incredibly high bar that we need to clear of beating a classical computer, you know,
Mhm.
at its own game, sort of, right? And it's amazing that we can ever do that. With AI, the scope of application seems to be anything whatsoever that human intelligence is applied to.
Quite accurate
Right,
indeed.
right. It's like
Yes, yes.
for AI to be useful, you merely need to match the performance of a mediocre human, you know. And
There you go.
and that's why this now that it's finally started to work, it really is changing the world.
The, so many good things there.
Hmm.
When you look, and I know we're wrapping up here in a
Yeah.
bit here, but I wanna get your take, and I know you had your blog
Okay.
post on with, the 2050 optimism,
Oh
2050,
yes.
right? So, when you look into the future,
Hmm.
what are you most excited about for either AI or quantum computing? But what are going to be the limitations to getting there?
Okay, well, I'm kind of idiosyncratic in what, excites me personally, right? But I mean, in quantum computing, I think what I'm most excited about, is not these modest advantages for optimization problems, whatever. It's not breaking cryptographic codes, it's not even simulating quantum chemistry and materials,
Mhm.
even though that would be kind of exciting. No, the most exciting thing for me is just disproving the people who said that quantum computers are impossible.
I love that. I
Like,
love that so much.
yeah, like there are still
That
these skeptics who say, this
yes,
can't be
yes.
right. Maybe quantum mechanics itself is wrong, or maybe there's there must be some noise, on top of quantum mechanics that will prevent you from ever
Mhm.
scaling this. I think given the experimental results of the last few years, those people have been boxed into a tighter and tighter corner, right? Like
Yes.
we can say to them, like, if this is not going to work, then why does it seem to work perfectly with like 100
Yes.
qubits and with thousands of gates, right?
Yes.
Like whatever new principle you believe in that's going to block this, why haven't we seen it yet? Right?
Mhm.
And, but, of course, we don't know for sure that nature really has this computational, ability, to,
Mhm.
like, factor enormous numbers and so forth until we actually demonstrate it. Okay, so I
Yes.
think, that really will be, not just, an engineering milestone, but a scientific milestone.
Mhm.
Um Now, in terms of AI, I'm both excited and I'm terrified, right? I think
Yeah.
those are,
Right.
both like totally reasonable reactions to like maybe one of the biggest transitions that's ever going to happen in human history, right?
Mhm.
Like we the amazing thing about the last decade, let's say, in AI is that there hasn't really been some amazing new idea.
Mhm.
Right? I mean, yes, there was the transformer architecture for neural nets, right? But the basic idea of neural nets goes back to the 1940s, right?
Mhm.
McCulloch and Pitts, right? People were trying, doing experiments with neural nets in the 1960s,
Mhm.
right? And then they discovered, a way to train, deep neural nets, the back propagation method in the 70s, in the 80s, right? And so these are all, I knew about all these ideas when I studied, computer science,
Mhm.
back in the 90s, right? They were
Mhm.
already sort of considered old ideas at the time,
Mhm.
right? But they just didn't give very impressive results. right? And, and there were a few crazy people saying, okay, but that's just because, we don't have the computer power to like run a neural net with, billions or
Mhm.
trillions of neurons, right?
Mhm.
Like the human brain has, or, we don't have, trillions of points of data to train them on. Right. And,
Mhm.
and this seemed like a sort of a wild speculation, right? Like usually, and when something doesn't work, scaling it up by a million or a billion, you know, just gives you a million times something that doesn't work, right?
Mhm.
But now, here we are, and like basically the crazies were right, right?
Mhm.
Pure scaling of the size of the neural nets, of the training data that we use for them, has been enough to, sort of grow these entities that we don't really understand any more than we understand our own brains, but, that
Mhm.
we can talk to, that can write code for us, that can, write, that, like almost every student in the world either uses to, do their
Mhm.
homework and,
Right.
write their term papers or else is sorely tempted to do that, right? And
Mhm.
so and like again and again, as we've been on this ramp up, right? There have been people saying, okay, but obviously it has to hit a wall, and and this next thing, whichever thing it hasn't yet done, whether that's first it was beating the human world champion at Go, and then it
Right.
was solving like math competition problems, proving new theorems, right? Whichever, is the next thing, right? That's the thing it won't be able to do. And look at these hallucinations, look at these silly
Mhm.
mistakes that it makes, right? And then this sort of, it's like we're in this storm, like with this sort of rising water level, right? And people just keep pointing to, but look at this thing, that thing is still dry, right? And
Right.
and then the water, rises and
It
subsumes
is
that thing,
coming.
and then, without blinking an eye, they're like, "Okay, but that higher thing up there, that thing is still dry," you know? And, the truth is that we don't know what the limit is, right? We don't know of sort of any, human intellectual work that, like, ultimately requires us that, maybe there is, maybe there's
Mhm.
stuff that we do that AI can never replicate, but if so, we don't know what it is, right? And so,
Mhm.
like, I think that, I would like us to be sort of approaching this with some humility about, the magnitude of what's being created, right? This is not just another consumer product, right? This is,
Mhm.
as far as we know, this is sort of the creation of a new, you know, intelligence on Earth, right? It
Mhm.
could very much exceed our intelligence as we, exceed the, chimpanzees or the orangutans,
Absolutely.
right? And that could go incredibly well for humans. It could also go incredibly poorly. So,
Mhm.
in addition to the quantum computing group at UT Austin, I now also run a group about theoretical computer science and AI
Mhm.
alignment, trying to figure out like what can we do as theorists to try to make this go well. I wish I had better answers there.
It's
Yeah,
I mean, there's so many questions and conversations
yeah,
left unturned. I mean, so
yeah,
many things.
yeah,
I know we have a hard stop soon.
yeah.
I'll give you could give a 30-second answer to my next question, but I
All
do want
right.
to thank you. Thank
Okay.
you for coming on.
Yeah, yeah.
Super.
Thanks for having me.
For those who are, lay people like myself and young people out there who are interested in the AI revolution that's happening, what is your greatest advice to them on how to properly interact with and have cautious optimism towards the future with
Uh,
regards to AI?
Yeah, well, okay, when people ask me like, "Oh, should I be, believing the hype about this thing, or should I be rejecting it as just all a bubble or as all false?" I'm like, "Okay, I would not even be asking the question in those terms, right?"
Mm,
I say, I would be asking the question, "What is true?" Right? Just try to figure out what is true rather than, this sort of vibes-based question of, how excited to be,
yes.
right? Because often,
Yes.
a new technology comes along, right? It will like have no effect on one thing, but it will completely change a different thing, right? And so you really do have to try to separate out the questions, right? And with quantum computing, try to click through to the original paper when you see a popular article, right? Because there is very often some just key thing that they're not telling you, right?
Absolutely.
This is probably good advice in general, actually.
Yeah, absolutely.
Yeah,
Well, Scott, thank you so much for coming on.
absolutely,
Super appreciate it.
absolutely. Yeah.
Where can people find you?
Oh, I'm pretty.
Follow you.
Yeah, I'm
You're
pretty.
pretty. I know you're pretty well. Google
Yeah, I'm
him.
pretty easy to find.
He'll pop up.
ScottAaronson.com is my
Okay.
homepage. I don't use
Perfect.
LinkedIn or anything like that, but I've got a homepage, and I've been writing a blog for 20 years, so people can check that out if they want.
Wonderful. Well, thank you so much. We'll
Sure,
talk
no
soon.
problem. Okay, talk to you later.
Bye-bye
Okay,
now.
bye.